Well, hello. Um, Today we're dealing with site-cast concrete. Most of the concrete that most people in construction will deal with will be poured on the job site for foundations, maybe in-place walls, other structures in concrete, sidewalks, driveways, patios, the slab-on-grade foundation for your building. And all kinds of other things that are poured on site where you create the forms and you pour it right where it's going to spend its whole entire life. That's site cast concrete as opposed to precast concrete. So that's what we're looking at here. So the slab on grade is where you're pouring concrete right against the ground. You could replace the word grade with ground and it would have the same meaning. Grade and ground mean the same thing, but often in construction we will say slab on grade. So the grade is the ground. As opposed to the other kind of slab, which is a suspended slab. So down here at the bottom, maybe we should flip them, I guess, but a suspended slab, or sometimes called a structural slab, it's suspended in midair. Well, not by itself, it's sitting on something. In this diagram we're looking at down at the bottom, we're dealing with a suspended slab that's sitting on top of a open web steel joist, or a bunch of them. And then you've got corrugated steel decking on top, and that's typically, most structural steel buildings are done that way. And then you've got a corrugated steel deck with concrete, maybe 3 inches worth of it on there or more. And so that's a suspended slab, or an example of a suspended slab. But any slab that's up in the midair where it's a load-bearing item, but it's not on the ground, it's a suspended slab. Here they're preparing the grade. If you're talking about a slab on grade, you've got to have really good ground because it's being supported by the ground. Often there's not really hardly any reinforcing on many buildings in the concrete slab. It's supported by the ground. They'll often put some mesh in there, but as my dad said, as a structural engineer, he would say that, you should tie a rope on that mesh so you can pull it out and use it for the next job afterwards too. In other words, what he was getting at is that this mesh is not going to help keep that concrete from breaking or cracking. It's only going to hold the broken pieces together. Okay, and if you want a slab that's not going to be wet, especially here in Louisiana, you need a well-graded crushed gravel of some sort down underneath. It's free draining, and that you've got a place for that water that does manage to get in there to drain away. And out of that, you end up with getting a solid dry base. And then we put plastic sheeting down. Generally, we're talking about at least a 6 mil thickness. Now, a trash bag or a lawn and leaf bag will be about 1 mil thickness of plastic. A contractor's bag would be twice as thick as that, about 2 mils. And so when you talk about 6 mil, it's pretty thick plastic. That said, ACI recommends 10 mil thickness on top of concrete. ACI is the American Concrete Institute. They're kind of the authority on concrete in this country. Members are, I'm a member, but it's made up of a lot of structural engineers and such. And people in the concrete business. So there you go. That's slab on grade. So here's a slab on grade, though, that's not part of a building. This is part of a building, and you need a dry slab. You don't care about a dry slab in the same way when it's a driveway. In fact, you don't mind if the water kind of migrates through it. It's not an issue. It'll dry out soon enough when the sun hits it. But so here we've got an example with edge forms, and that's the nature of driveways and sidewalks, as you end up with little edge forms, usually not even with a thickened slab at the edge, whereas a slab on grade concrete slab, like back at this picture, will typically, if it is a foundation like we have in Louisiana where it's actually supporting the walls, it'll be a thickened slab. But this picture here, you can see a basement wall back over there in the background. So that basement wall is sitting on a foundation. So in those cases, even then, the slab on grade inside of a building like this is just 4 inches thick. It's not thickened at the edge. If anything, it's a floating slab. It's not really structural in that it's not supporting loads, vertical loads, but it is generally structural in that it's pinning the bottom of that basement wall to keep it from kicking in from the load of the dirt behind it if it's backfilled against. Okay, more detail. We isolate anchorage points in walls. If you got something like a post, a column, whether it's made of wood like this, which is not likely to be useful outdoors in Louisiana, but you might have a piece of pipe that's a column, or even a concrete column that's going down through that slab to a pad footing or something. In that case, it's an anchorage point, and so then you need some expansion material around it so that as the concrete moves around, and concrete does tend to move around a little bit from side to side, that it's not going to end up either dragging that column sideways or causing the concrete around it to break up. And then you got a problem here where moisture and critters can come through and everything else, and unsightly cracks. So here's the vapor retarder. Some people will call it a vapor barrier. It's actually a moisture barrier, but a vapor retarder is the more correct term. So here on this page, I've got actually what I just finished saying, how, we want 6 mil minimum. That's what the building code requires. Now, really high-end energy efficiency standards on buildings like the Passive House standard will recommend 15 mil. So not just 10 mil like ACI is asking for, but even more. You're talking 15 mil is getting to be 2.5 times more than what the building code requires. So the idea is to have no moisture, no cracks or slices or broken parts in that plastic so that moisture can find a way through, so that you end up with a dry slab. It reduces your air conditioning load when you don't have moisture coming up through that slab. Okay. Here's an example of plumbing coming through, and we got a seal around the plumbing too, where it pokes through and comes out of that plastic sheeting, or visqueen, as we like to say. Visqueen is just a brand name, a local brand name for plastic sheeting, polyethylene plastic sheeting. And so then we might be putting mesh up there, but it really should be chaired up. It's amazing how rarely mesh gets chaired up, though. We lay it down and we're supposed to pull it up with the come-alongs, but in reality is most of that mesh, it doesn't even end up in the concrete at all, even though it wouldn't keep the concrete from breaking if it's in there, but it's basically useless when it's sitting there down in the dirt underneath the concrete slab, just causing rust. Okay, you can tell how much I don't like mesh. It's a joke. You need about 5 times that mesh in a 4-inch slab if you want to keep the concrete from breaking. And how do you keep that in the concrete and not sticking up out of it? So it's a problem. Just use rebar and be done with it. Okay, but it's not always your choice. You're not always running the design on it. But if you're ever building your own house, don't use mesh. It's a joke. It's an old carpenter's tale. It doesn't work. We use welded wire fabric or welded wire mesh oftentimes in concrete, and sometimes if that's what's specified, that's what you have to use. You're not the engineer, then you don't get necessarily choose. But if it's your own building, if it's your own house, you can ask for and use rebar, and then you've got a much better thing. First of all, when you're standing between the specs, you got more space between rebars to stand as opposed to having to stand on the rebar. Whereas in the mesh, you're probably dealing with no bigger than 6-inch by 6-inch squares, and so you can't stand anywhere but on the mesh. Okay, I digress. You're also not supposed to let concrete drop very far. If it's coming out of a concrete chute in the back of a ready-mix truck, like this bottom right-hand picture, well, then you need to have you don't want it to drop too far. No more than 4 feet maximum. Same thing when it's coming out of a concrete snorkel of a concrete pump. You need to keep that pump nozzle down low so that it's not dropping too far. Why? Because if it's dropping from too high of an elevation, the gravel and the sand and the paste will separate from each other, and then you've got problem on your hand where you've got rock pockets and you've got paste pockets, and none of that's good. It makes for weak concrete in both cases. And here they are pouring the concrete on a driveway that's actually running downhill. And they're getting ready. They're placing more than they need, and then they start screeding it like this. So a 2x4, like they've got here, is called a screed. Now, most of the time, a 2x4 is going to be long enough to reach from one side of the form to the other, and actually a little longer than that, so you can run it side to side as you tip it slightly forwards, or actually, no, tip it slightly backward, I guess, if you're looking at from the direction these two people are at. And they don't always stand in the concrete. If it's long enough to go from side to side, they could be standing on each side outside of the concrete and actually screeding it across the way that way. And then you try to keep a little bit, not very much, but a little bit of concrete in front of it so that you make sure that when you're striking it off, you're not creating pockets or depressions. So there are 3 phases or 3 steps to finishing concrete. You got to get it in the form, and just get it at the right elevation. So that's the strike off stage. And that's what they're doing with a screed, striking it off. And it's not like you're smacking it with something like you're striking something with a baseball bat. You're striking the surface to the slope it's supposed to be. If it's supposed to be a perfectly, if it's a house slab, if it's a building slab on grade, well, then you want it level. And in many cases, you want level in the footings and everything else. But if it's a driveway like this, well, then you want it to be running at a slope because you want to send the water somewhere. So we always want outdoor slabs to have some kind of a slope on them, about a 1 or 2 degree slope, about a 1/4 inch per foot, 1/8 of an inch to a 1/4 inch per foot slope, that kind of thing. Here's another kind of strike-off process with screeds. Anything that's striking off the surface is called a screed, so these are all considered screeds in all 3 of these pictures. You've got a vibrator mounted to a straight edge here up at the upper right-hand corner. Over at the upper left-hand corner, you've got a vibrating screed where it's a whole superstructure running across the whole lane or roadway or whatever it is. And these things can oftentimes be contorted so that they can have a curve to them. If you're going around a kind of a corner, they might bank it or some way. And then this bottom picture is a much more elaborate piece of equipment that is a screed and a floater all at the same time. So it's doing the floating. So when I go back to the original page, we got these 3 stages. I didn't really elaborate yet. I usually say this first. Grumble, grumble. Anyways, yeah, so this first is the strike-off stage, which I've been talking all around. Then we float it, and then we trowel it. We trowel the concrete last. If you trowel the concrete and skip the floating stage, you'll work up too many fine materials to the surface before the excess water in a slab. There's always excess water in the mix that you don't need, except maybe for placing, especially if you don't have any additives in it. The excess water that you add to concrete will weaken the concrete, but you do need a certain amount of flowability and workability in the concrete in order to get it placed, especially in a slab. Whereas in a wall form, you can have a stiffer concrete mix with less water in it. And of course, I've talked about in the concrete technology section, I was talking about how we can use additives that make the concrete behave as if it's got like extra water in it. But in true force, it really is, with behavior and actual water are 2 different things. You can have what we call water reducers of various kinds. Super plasticizers are the complicated, more fancy, more tricks being performed in order to make it act as if you've got more water in it than you do. Okay, so we look at the floating next. Here they're floating the concrete with a bow float. The most common way that we float concrete is with a bow float. It's about 4 feet wide. Typically, there are some that are 42 inches. Most of them are 48 inches wide. And you have it connected to a bunch of extension handles. As you've got it tipped the way he has it, it's a little high, a little aggressively tipped. You're pulling it toward yourself, and then you tip it the other way as you're pushing it away from yourself. But usually really close, maybe only a couple of degrees off of the off of the slope. Not as aggressive as this picture. So I probably should find better pictures of somebody using a bow float. But you run that thing 90 degrees to the way that the strike-off process was going here with the 2x4. Now, you don't have to use a 2x4, as I showed you some other screeds, but I've seen some professional concrete finishers that have something that looks like a 2x4, nice and perfectly straight, but it's actually made of magnesium. What you never use is a material for troweling or floating or for screed or any other concrete tool. You never use anything made of aluminum. Aluminum violently reacts with concrete, so any little specks of aluminum that wear off into the mix can cause a pocket of expansion. And so, we do add aluminum as a very, very carefully into a mix, very evenly distributed, but you don't want a chunk of aluminum coming off as it's wearing while you're going back and forth with any kind of a tool. So there's some floating. Here's some more floating. At a smaller level, you use short hand tools. And so this is actually a longer version. Most hand floats are going to be about 18 inches long. This is getting closer to, I would say, 3 feet, maybe 2.5 feet or something. But so anything longer than 8 inches, anything longer than 18 inches. Sorry, I have trouble this time of day, I guess, with misspeaking. But it would be considered a derby, so which is kind of a funny little term. It sounds like a hat or something. I don't know. But anyways, either way, anything that you're using that's made of wood or magnesium, and those are the two materials that we make floats out of, would be considered a float in the floating process. You don't want it too smooth. It needs to be a rough enough material that you're not sucking too many fine materials to the surface. And I didn't finish my statement about that either. And that is that when you work up too many, if you start troweling and you work too many fines to the surface early on, then you trap that excess water, what we call the free water, underneath that layer. And then you'll have chunks breaking off over the years after that on that finish. So the idea is within the first 30 minutes or so after placing the concrete, you will get a lake of water that will come to the surface. Unless you don't have any plastic sheeting underneath, and it might get sucked up underneath inside into the ground. And so you may not have as much free water then. But so in the floating stage, you do it right after you've screeded, and you're working a few fines to the surface. It definitely is smoother, but you're also filling holes. You find holes, you might be taking a shovel full of concrete and placing it in there where there's a depression, trying to keep this thing as flat as possible. And then you also do some float edging first, and I should find some pictures of actual floating tools. They're not going to be made of sheet metal, of stainless steel like you see here. The true floating edger will be made of bronze or magnesium, again, a coarser material that you're just roughing in the edge to push the gravel pieces in. And so if you're edging, then you're going to be doing some float edging first. But once you finish floating and troweling, you'll be filling in the areas that you floated. But the whole goal is to move some of the chunky rocks in deeper, away from that rounded edge that you're trying to make, if you're trying to make a rounded edge. So edgers and groovers are used to create neatly formed, well-consolidated joints and edges in the slab surface. But you have to start by roughing them in with a float edger or a float groover first, and then later, when you're doing the finishing, you can come back and retool those joints with a finish edger. And then we use power trowels, not so much for floating. This is kind of something that maybe I should change the stuff in this page, but if you can get a power trowel on top of the concrete, this concrete is not freshly poured. It's been there for a while. And so it's setting up to the point where, if it's getting away from you, you might put what they call float blades on a power trowel to aggressively pull up more. They're going to be much sharper angles, but they're meant to pull up more fines if your finish is getting away from you. But understand, when you use a power trowel for floating or for which is a later stage, you're already in the troweling stage. And so it's still troweling at this stage. It's not really floating per se. And when you're when you're troweling the surface, at that stage, you are working up a lot more fines to the surface, and that is not making that concrete finish stronger. It's making it smoother, but not stronger. The strongest concrete surface you can make is to just place it and strike it off and float it, declare victory, and go. Stop messing with it. So with roadways and with parking lots, with driveways, with carport surfaces, we really don't want to make a super smooth surface. We don't really want it smooth. We want it to be flat, but soon as you finish floating it, maybe you put a light or a coarse, depending on what you're after, broom finish on it to give you some traction, but you don't want to keep troweling it. That's actually, the more you trowel and mess with it, the concrete's setting up as you go, and you are making it weaker, not stronger. You are making it flatter, though. And so inside a house, we don't need as strong a surface on the concrete generally, but we do need to have a flat surface for the flooring. We need it to be flat enough that everything, any kind of flooring you're going to put down will be nice and laid properly. And so that's an important function, but you certainly aren't making the concrete harder by troweling and polishing it. That's not what you're doing. You're trying to make it, so anyways, let's stop that process. Here that guy is doing some kind of troweling on a stick. That's maybe about as much troweling as you're going to do, maybe fixing a little smudge or spot maybe. But in general, the more you mess with outdoor concrete, the worse you're making it in general. So the troweling, there's usually not much troweling on an outdoor slab. You might do more on a garage floor because you want to be able to sweep up stuff, and you want it a little bit smoother, but you certainly shouldn't be doing super flat floors on a garage generally. We want now there are cases in warehouses where they want a super flat floor, and so they want extra troweling, but they also want it to be a super hard floor, and they'll actually trowel in some hardener. Is a kind of a powdery dust that they'll sprinkle on the surface, and they'll trowel that in order to give you a super hard finish. And sometimes they'll even have a coloring in there so that their shop floor or their warehouse floor actually has a color. But most of the coloring that's put in concrete is actually an acid wash instead, where they acid etch it instead after the concrete is fully set up. Okay, let's move along here. Other finishes, I mentioned the broom finish, and on an outdoor slab, a broom finish is the preferred way. There's sometimes some re-straightening that'll come around with a straight edge drawn over the slab to reduce minor undulations. I mentioned the shake-on hardeners. Dry powders can be floated into the slab to create a harder, more durable surface. That's important because the more you float it, the weaker you're making. So by adding the hardener, you're helping to combat that, to get a harder surface. And there's even laser-guided screeds that can be more precise in finishing that slab. And that's what we would have seen back in here, wherever it was. Yeah, this machine would, I'm sure, be laser-guided. And there's some other cases like that. Okay, let's see about finishing in the winter time. We've got to do moist curing. In the summertime, we want moist curing. In wintertime, we want to keep the concrete from freezing if you're in an environment where that's a problem. In Louisiana, there's not too many days a year where you have to worry about the concrete freezing. That comes up every now and then, but it's not a common issue. A lot of times you see the weather coming, you don't even bother pouring concrete in it. You wait a few days and things change. That's the way it is in Louisiana. But in colder climates, cold winter kind of pouring, you may have to build tents around the whole thing in order to run heating. And you have to, in summertime and all year round, we have to worry about the concrete drying out before it gets strong. And so normally, the very next day after you poured concrete, you will hose down the surface and cover it up with plastic to keep moist curing going. I've talked about that in the chapter on concrete technology. But anyways, and then we have to control where cracks happen to have a nice straight line. You don't want this wandering line like you see on the right-hand side. First of all, you end up with little broken up pieces that'll fall out, and you'll have an uneven surface. And as there's more movement in the concrete, you can end up with more broken up places in here. You want a nice straight line, and then you can control it, and then you can also control, if it's outdoors, to keep water from migrating through from up top on the rainwater to going underneath the slab and washing the soil out from underneath that slab. So cracks happen, so we want to control them by keeping them nice and straight. So it's normal that we do things like saw cuts. And so if you poured concrete early in the morning, you might want to get saw cutting that afternoon or that evening. If you poured it throughout the day, it'd be the very next day. You want to get on that thing with a saw to cut through. You want to cut 1/4 of the depth of the slab. We talked about that in the concrete technology chapter 2. So here we've got an example where you see a controlled joint. It's a tooled joint where they ran the groover across to kind of groove down. You want to cut 1/4 through, 1/4 of the thickness. So if it's a 4-inch slab, you want to cut 1 inch in. If it was a 4-inch, if it was an 8-inch slab, you want to groove in 2 inches, or else groove from underneath, maybe with a divider that you installed ahead of time. And that way you only have to tool in or cut in 1 inch on the top, But you see on the right-hand side here, similar thing. It's wanting to crack in the same spot. It should have been tooled also, really. Here, when we have an anchorage point like a column, this looks like a concrete column, that's going down to a pad of footing underneath or something, then we got an anchorage point here that's going to cause concrete to kind of break up. And so we will put a diamond around this thing and align the control joints to the tips of the diamond on all 4 corners, heading 90 degrees from each other, heading out. And then the diamond box will typically have expansion joint material that it's made of so that it keeps the concrete from dragging this column from side to side. It's an important process. So you'll see lots and lots of diamonds out there around columns, light poles in parking lots and everything. Now that I've mentioned it, you'll start seeing them more often if you haven't noticed them before. Castering a concrete wall. Well, with wall footings, you got to start off by having a foundation for the wall. And so it's very common to have a continuous footing going all around the perimeter of a building, especially for basements. But anytime you have a wall, you typically need a footing underneath, and that footing will be typically wider than the wall is, at least twice as wide, depending on what quality of ground you have. If we're putting a wall footing down in Louisiana, it's probably going to have to be 3 or 4 times as wide as the thickness of the wall to support it, depending on how heavy the loads are. So you're going to have the continuous footing will be at least 16 inches wide, but it could be 3 feet wide. It just all depends on what the loads are. And then you need rebar coming out of the footing. That's what this vertical rebar that they've got capped, so that when you fall on it, you don't get impaled by it. And then they will typically have either a rough section underneath the concrete wall on that footing, or they'll have a keyway in there. So let's see if I can see some pictures here. This drawing on the left is showing you a little dowel sticking out of rebar. They're made usually of actual reinforcement bar with bumps and a whole bit on them, that are tied to the mat of steel down below in the pad or the continuous footing. But then there's a keyway in the middle. That could be kind of a beveled piece of wood cut at about a 5 to 7 degree angle on each side, so that you can get it out afterwards. If it's just if you just sink a 2x4 or something in there, you're going to have a hard time getting that sucker out of there, because the concrete literally shrinks inward, and so it's going to lock that sucker in. So you need it to be beveled on an angle so it can slip out afterwards. But it's not necessary for it to be a keyway. It could be just chopped up rough concrete. And so that's another way to do it. Depending on the engineer and what their real experience is with concrete, the traditional textbooks show a keyway like this, and so a lot of engineers go and try to put that in there, and they can, but it's not always necessary. And if it was a water tank you were building, then you might have actually a piece of heavy rubber that might be 12 inches wide or 8 inches wide, and you sink half of it, a ribbon of this stuff, half of it in the concrete footing, and the other half is sticking out so that it can be embedded within the concrete in order to keep water from migrating through that joint in a water tank. You see on the right-hand side here a double mat of rebar two walls of rebar here. And so it's a vertical mat, but it's a mat. And you also probably notice that there's some things sticking out through the form. There's one concrete form already placed there on the other side of this, these two mats of rebar with form ties poking through. And those form ties are ready for you to go and take the second wall form after you've got all the rebar and anything else that needs to be in that wall. Then you can fish all those form ties starting at the bottom and working your way up through some holes in the other form in order to hold those two forms in place. So the form ties are what hold the second form in place by heavily bracing the first wall form. So here's some more reinforcing standing up. And so sometimes the reinforcing is such that it completely can stand up on its own if it's heavy enough rebar. But there's other places where you need the rebar to be held in place by being kind of tied either to the form ties or to the wall in some fashion to be braced to keep it straight up and down because it's a little too floppy to stand up on its own. Here's some more heavy rebar. Maybe as a heavy shear wall, and this would be a heavy shear wall in a building too to keep it, the very, very important structural element. In smaller jobs, the form ties will look more like this, and the forms will look more like this. Where you have wood forms, you'll have studs, and so my cursor is pointing to a stud here, and there's another stud here. You have a whole bunch of studs that might be framed just like a framed wall that in a house, where you might have them on 16-inch centers with plywood, and the plywood would be what you actually pour concrete against. And then they'll have maybe a bottom plate and a top plate framing it and stuff. And then the form ties come out to whalers. So these two 2x4s that you see here and over here will have a wedge behind them that's holding the form tie in place. And so these form ties will be made for a very specific size of wall. Let me get a sip of coffee. I got a frog in my throat or something. Oh, the coffee solves all problems here. I know my wife would say I need to have water here next to me instead. But coffee or nothing. Okay, let's see. You also notice these form ties have little little plastic pieces in here. Those are meant to create a little belly button in the wall. This piece of steel runs all the way out from the whaler to whaler here on these wedges, and then you're getting your 6-inch or your 8-inch wall defined here by the form tie design and how it's designed. And once you pour the concrete and it's gotten strong enough, we'll come out and we'll break that form tie off. We'll take the wedges loose, the concrete forms loose, and then that wire will get snapped off so that the little piece breaks off over here in the bottom of that, like you see in this picture right here. And so that's a really common system. It's very, very common in walls nowadays. We had nowhere near this nice of a form tie when I was growing up. And then we literally end up with a whole bunch of these things. So you can fill them up with a grout afterwards if you need to. But when I was growing up, we had metal ties like this, where we had to smack them and break them off, but those would just break off just below the surface in the concrete, and sometimes not even that far out. And they were pretty cheap and kind of annoying. They're very sharp sheet metal pieces, but they worked in a similar way. Okay, here's some forms in showing you exactly what we were looking at basically here. All these little wedge pieces that are holding all these whalers in place and the form ties, and you can strip them. Now, some form systems have a threaded piece, a male threaded piece that goes in the wall that'll be poured into the concrete, and then some female threaded pieces that go in on the outside. And the idea of those kinds of, they call them she-bolts, but they're calling them bolts, but those are really the nuts on the outside that you're screwing on both sides. And the idea is that you can unscrew them and then move the form and clamp it back and screw it again. And so it allows you, they use that a lot of times in slip forms, concrete slip forms, so that you can reclamp them to keep jacking up the forms and reclamping them against the existing concrete and pour some more concrete and keep going. Or sideways, if you didn't have enough forms to form the whole thing out, you might pour some of it and then reclamp it. And so that's a system that's used sometimes. Here's some steel forms. They're so heavy that they have scaffolding built into them. So that's a good system to have, for scaffolding. But it's a heavy enough thing you would never physically pick these things up. These would be picked up with a crane instead and put into place. Even if you're picking them up to do some slip forming, you do that with a crane or a jack of some kind. Here's some more forms used here. They're a combination of, they look like they're steel forms. They might have plywood on the actual surface that the concrete's poured against. But we typically heavily brace one side of the form. The other side of the form gets put in last after you've got all the reinforcing in place, and then it gets held together by the form ties. Here's some more slip forms for maybe an elevator shaft or a silo. I'm not sure which. The elevator and stairway shafts in a high-rise are often built this way as they go up and up and up, and they keep pouring more. And then they'll have the she-bolts with the bolt sticking out still so that they can reclamp them, and they can also use them if they built this thing strong enough. It might be part of the design that the steel structure is actually bolted to it so it becomes a shear wall at the same time. Here's some more steel forms for a basement of some kind. And here's some basement walls of some kind. Here's some more. And you see those openings that are blocked in and out of wood. Those are meant probably for some kind of building services like plumbing and water lines and such to penetrate through the side wall of the building to get them in there. More pictures in here. Here's a bit of a screw up here where the form somehow let loose on a repour or on a slip forming, and it didn't quite clamp like it should have, as tight as it should have, and they end up with this excess line. Well, you can come back and patch those walls up to parge it up to hide that difference. So as long as you've got some white glue, maybe as a concrete fortifier, when you buy it where it's already pre-mixed with water, that you can spray or mop it on the wall, and then you can, with a sponge or something or a rag, once it's dry, maybe 15-20 minutes later, you can then patch and parge a concrete mixture on that surface with some rubber floats or some rubber gloves and kind of smooth it all out and make it look pretty. So you can always hide stuff like that. But something like this is a more messed up thing. And so in something like this, we will typically install a dry pack grout in here where we mix concrete up, basically that's maybe a zero slump mix with just enough water for the chemical reaction. We can pack it in there without a concrete form, and just with rubber gloves you can go and pack it in and smooth it out and make it look pretty. And it's the kind of thing you want to do as soon as you can before anybody sees it. That's the rule. We don't talk about Fight Club. We don't talk about concrete flaws like this. We just fix them. And so smart contractors are ready with the material to fix those kind of problems ASAP, as soon as they possibly can. It's amazing how repairable concrete is. Okay, here's some flaws in this retaining wall where they don't have proper drainage behind it. And so all these cracks in the wall are showing water migrating through. Well, some of these cracks are probably forming because of the excess forces of water. The force of water doubles the forces behind that wall. And so it's another reason why you normally have to have drain rock behind those walls and drain tile to send that water somewhere else to reduce the hydrostatic pressure of that water on that wall. There's another system called ICF, or stands for Insulating Concrete Forms, and they're made typically of a bunch of styrofoam Lego blocks that are glued together, and then they can fill the whole thing up with concrete. And the thing is that these forms stay behind. They stay as part of the structure. So you basically end up with your insulation, an insulated concrete wall that's insulated on both sides, and it helps to hold this thermal mass inside the building. So that's a pretty good system. And then I've talked about this a little bit in the concrete technology area, but here's a good example of some tilt-up concrete walls. They're basically precast concrete walls, but we call them Sitecast sometimes because they are cast on the site. It's just still a precast item on the job site, though. And the idea is what you're seeing in the background are the walls, and these walls are generally poured right up close to where you need them so that the crane doesn't have to reset. They can just pick up the item and put it right where it's supposed to be. They have weld plates, and that's what you're seeing in the background here. There's a whole bunch of these weld plates here and here, here, that are in each item so that when they match up next to another panel, they can be welded to each other. They also have to be braced, and so here we're not seeing any picture of braces, but there is a brace showing up through that doorway opening on the other side, so that means they must have been able to brace them on the other side somehow. Anyways, casting concrete columns. Gotta watch my time here. Concrete columns, they start off with a pad footing. So the pad footing has the rebar mat down near the bottom. In general, we need that mat of rebar to be 3 inches off the ground so that moisture that's in the ground doesn't soak up through the concrete and rust the mat in the concrete. So it needs to be 3 inches off. But otherwise, if it wasn't for that, we'd want it about inch and a half off the ground. So, of course, if you got really, really, really dry ground, then maybe you don't have to worry about the moisture issue. I mean, I don't mean dry today, but I mean always. So in Louisiana, that's not a thing. Ground is wet most of the time. But in some sandy desert areas, rusting of concrete of the rebar is kind of never happens. Okay, here's some vertical columns, and the steel in columns is always very heavy, particularly the vertical steel. Then they'll have the horizontal stirrups. We call them stirrups in here, that are wrapping around and encasing. So the vertical steel is going to be inside the stirrups, and so we tie them at the corners and in between, wherever, like we do here. And of course, in that round spiral, there are no corners, but you get the idea that it goes inside, it gets encased. The stirrups add to the compressive strength of the concrete column. The vertical steel is the stuff that's in tension as that column is being twisted or bent in any way, whatever the forces are that column is holding. The vertical steel is meant to take those kinds of tensile forces. There are various versions of the patterns in the concrete column depending on the size and what the forces are. Sometimes you can get so much steel in a column that it gets to be pretty congested, so you have to pay attention to what kind of concrete mix you're supposed to be using with that concrete column. You may have several concrete mixes on your drawings, and you got to make sure that when you're pouring concrete for this column that you're using the column concrete that was specified for it. It might have to do with the size of the aggregate to make sure it will fit between all these bars. So here's a bunch of columns in here. Here's some column steel meant for something like this. It could be picked up with a crane and tied and attached to the, if you're going up and up and up with these columns in a cast-in-place column building. But a lot of the time the rebar is tied together in these fashions at a steel fabrication shop that specializes in this, so they're already ready for you to pick up with a crane. But I've been on plenty of job sites where we literally had to tie all this steel ourselves. Here's some clamshell concrete column forms that are being brought up and picked up to place around it, and they'll connect them together and brace them properly. You need at least, at the bare minimum, 2 braces on each of 2 sides that are 90 degrees from each other. So as you see in this picture, they've got 2 braces right here on this side, and then 2 braces. You can't see 2 braces, but there's got to be 2 braces over on this other side, 90 degrees from it, so that this column will not lean one way or the other or twist. If it can twist, it can lean. So that's why you can't just use 1 brace, because if it can twist, it will lean. Okay. OSHA might not like how they're tied off here, but anyways. Now there's another system here of 1-way and 2-way floor systems. So a 1-way floor system is where you've got these long, narrow bays. Right here, we're looking at a bunch of ribs in here. And so these are acting like joists, and so that's a 1-way floor system. 1-way floor system. Now, if you've got a rectangular bay in here between the beams and joists that's more than twice as long as it is wide, then that's a one-way slab. They call this a one-way solid slab because it's pretty solid. But actually, there are slabs that can be much more. This is more obvious. You got these long, narrow bays on a rib slab. So the rib slab is the perfect example, the simplest example of a one-way slab. All the principal structure of supporting is going one way. Well, you might say it's going left and it's going right, or to and fro, or whatever. But no. It's the point is it's like ceiling joist in wood framing, or floor joist in wood framing of 2x12s. That's considered one-way system, and it's going, across, in that direction, as opposed to going both ways in that sense. So here, that's showing an example of how they would make a one-way rib slab with a bunch of these steel pans that are placed in place on a upper support system, kind of like a fancy heavy-duty scaffolding system over the whole property. And they're spacing these out, and they'll eventually pour concrete in here in all those areas after they get all the steel in place. This is a wide module. It's still a two-way slab system. I mean, a one-way slab system. But I want to show you the two-way. So first of all, the definition, I've already said it out loud, but I didn't have this diagram before to show you. So if the length of the bay is at least twice as long as it is wide, then it's a one-way slab, rectangular bay. If the bay is anything less than that, and especially if it's just a square, then it's definitely a two-way slab. So here's a two-way slab because these bays, the space between the various beams is pretty much a square. That's very much so. You can have a flat slab that has no bays, and that's a two-way system. Now the reality is there's a couple of things to point out too, is that these columns have those cone-shaped looking tops to them. They call that a mushroom capital. And then the panel around here is called a drop panel. So the comment, you can have both, one or the other or both, but they're giving you more room to transition to spread the rebar tentacles out into that flat slab up there. But it's considered a two-way system also. So then it's what you see internally inside that flat slab is a heavy beam created out of rebar in the slab itself, basically. And so that's what's going on here. They got that drop panel. They don't have a mushroom capital here, but they do have the drop panel, and that's giving them a way better way to distribute that load out further on that slab. And this one doesn't have anything. It doesn't have a drop panel, doesn't have a mushroom capital. So you wouldn't use something like this design probably to build a parking structure. Would have to, but you might be able to get away with using this for slabs that are supporting condominiums where it's just people inside. There's some shear pins that the arrow is pointing to, and this is got a lot of post-tension cables in it, and then some other rebar. But the shear pins, you could have a steel beam that these things are welded to that is supporting this concrete slab, and those shear pins help to join the steel girder to the concrete by having those steel pins welded to the top of the steel beam, and you can get a good connection. So once the concrete sets up, those pins with those heads on them really help to connect the steel beam to the concrete slab. More examples of a two-way slab. Here's a better example of one. You don't see any joists of any kind in here. And then maybe the perfect textbook example of a two-way slab is a waffle slab. If you have a good imagination, it kind of looks like a waffle from underneath. It won't look like this on the top. And then they actually have a drop panel, the equivalent of a drop panel around these columns by filling in and not having waffle pieces in this area, but it's solid. It gives them more strength underneath this column. We actually have waffle slabs over at, you can see them, they're made to an architectural feature in some places in the Acadian site, the Acadian buildings, over at the Acadian buildings on Acadian and Winburn for BRCC, you have, if you go in the front entrance off of Acadian Thruway, you can go in there and see these waffle slab shapes up there in the ceiling. They've decided to make them in a feature when they remodeled the building. So if I ask you about the waffle slab, well, that's definitely a two-way slab. The rib slab, that's definitely a one-way slab. So these are things that you'll see on possible test questions coming up for exam 3. So here's a waffle slab in the flesh, and you see those big mushroom capitals on that column, and they've got a kind of a drop panel of filling in the spaces. You hit one of those things with your truck or your car, the column is probably not in any danger. It's just your truck that's going to take the beating, or your vehicle. So yeah, very husky columns. They like to do that because then they're kind of invincible. But boy, it sure can tear up a vehicle. There's some more slip forming going on here. There's some more of that, and some steel basement walls. There's a basement wall being formed of some kind with the old-fashioned form ties that I hate so much, that are made of sheet metal. They're really, really hard on the face when you hit them, when you get them in your face or in your eye or whatever. So once you get those form ties in, you want to be ready to put that in the other wall side form in there as soon as possible, so you're not going to be hurt, torn up. Shoring and reshoring, you know, the idea is that when you start having a steel beam, a whole bunch of steel beams, and you're holding up, and you got corrugated steel decking like you see up top here in this picture, then you start pouring concrete. That concrete doesn't add any strength to the floor system at all at first, because it's just dead weight, and it can cause it to droop. And so what we do is we put a whole bunch of little mini columns in there to hold it up temporarily until the concrete has gained strength. And once it's gained strength, it's got that exoskeleton at the bottom of the corrugated steel decking that it was formed against, it was poured against. Once they bonded to each other, they worked like rebar and concrete together to make a nice stiff section. And so then you can finally, once the concrete's gotten strong, you can pull these posts out. In the Hard Rock Hotel collapse in New Orleans, they ended up with they started pulling these reshoring posts out too early, and that's really what caused this building to collapse. It wouldn't have collapsed if it wasn't for that. You can find a half a dozen contributing factors, but that's the primary one, no matter what they say. We had colder weather. We hadn't had any cold weather, and all of a sudden we do, and suddenly this building collapses. Yeah, they were pulling these things out too early. There's a whole bunch of the reshoring posts in this picture too. They're not from the Hard Rock Hotel, but this is what it kind of looks like. They get a whole bunch of these things in there, and then they were pulling them out too early for that building. There's some more pictures of things I think I've shown. The vertical slip forms are common in industry. We use them all the times. There's some forming work. There's some more precast wall panels. So when we're talking about tilt-up panels, we also, sometimes people will call them lift slabs, but really most people in the industry do not call the tilt-up wall panels lift slabs. The lift slabs are horizontal slabs. And so in lift operations of lift slabs, what they do is they pour all the concrete slabs one on top of the other, and then they jack them up afterwards. So lift slab operation here, we've got a slab where all these slabs were poured on the ground, and then they're hoisted up into place. So as they hoist them up and lift them up into place with hoists, they're called jacks, but they're really a hoist. They have to be careful that this thing stays stable, because the problem is you can't have a bunch of diagonal bracing to make it rigid, because all these floor slabs are moving up through the columns. So all they can do is hoist them up to the first floor and really heavily brace the ground floor, and then hoist them up some more and start bracing them again and rebracing as they go. So as they go up and hoist them up, they end up eventually the building. So that's one system for lift slabs. I talked about the safety aspect in the safety class of lift slabs. Here we've got some heavy cast in place concrete that is kind of getting on the stage, that is so fancy and impressive that you might think it's precast, but it's so big, that's the only reason that you might realize it's not precast. Now, I've seen a few big things that are precast and managed to be used, and up where I lived in Canada, we have this floating bridge with anchors, floating concrete bridge that is held from floating away with concrete anchors. And the concrete anchors are the size of a 2-story house, and there's maybe, I don't know, 60 or 70 of them. I really never knew how many. See if I can find out. But anyways, they were maybe not as big as this, but they were pretty darn big. But the reason that they could pick them up and move them is because they poured them right next to the shore, and they were able to literally drag them out on barges and take them out where they needed to take them, and then take a pair of barges and there's one big anchor, and they can drop it down where they needed to in the water, where the lake is like 1,000 feet deep, so they had to have some very long cable. Okay, there's that same bridge here I was looking at, though, but here's showing where you're looking at the cast in place part here, and then the precast girders are right here, and they got kind of floating barges that are picking up these big precast elements to put them in place. So this is right there on the Potomac near Washington, D.C. I'm not exactly sure where, but somewhere in the region. So I thought it was a pretty impressive structure. So there it is, the bridge. Again, it's not like it's way up in the air like our bridges here in Louisiana, because you're not trying to bring a lot of big ships in here. It's not that kind of river. Anyways, impressive enough. Okay, well, now we're going to move on in our next topic, dealing with precast concrete, and that'll be a much shorter topic than this one was.